Cool. So hello everyone. So I guess I should start, right? Thank you very much for inviting me to give this talk. Today I'm going to talk about a project that I did in the early stages of my PhD. So as a reminder, I'm a PhD student. I'm supervised by Professor Arthur Gretton in the Gatsby Computational Neuroscience unit, and I mostly work on kernel methods and generative models. I guess is my first point of interest. And what I'm going to present is the result of the first project that I did, which is a joint work with Michael Arbel, who's now a postdoc at INRIA, and that deals with the KALE flow, which is a relaxed Kullback Leibler gradient flows for probability distributions with disjoint support. So I'm going to unpack all the terms throughout the presentation so that I hope by the end it's pretty clear what it means, even though it may sound a bit obscure at the beginning. In the summary, we introduce KALE, K-A-L-E, which is a probability divergence that interpolates between two famous probability divergences, that is the Kullback Leibler divergence and the maximum mean discrepancy. And we're going to study the Wasserstein gradient flow of this divergence, which is a very natural object to study when you look at the inductive bias of probability divergence. And we can see this Wasserstein gradient flow, if that makes sense to people, as an extension of Langevin diffusions to the cases when the target measure doesn't have a log density. So as I said, it's going to be a bit clearer later on. So I'm going to start with first giving a bit of background on probability divergences and make it clear how KALE is constructed. And then I'm going to also discuss a little bit like what are the use cases of KALE in generative modeling especially. So first a little bit of background on probability divergences. I hope that anyone feel free to tell me if you're not familiar with reproducing kernel Hilbert spaces. Is everyone familiar with RKHS here?
I fear that most people here aren't, but I am.
Okay. Okay.
But I think.
Okay. Yeah, that's a bit what it's because it's so central in my research that sometimes I forget that some people actually are not working with this kind of thing. But sorry. So so reproducing Hilbert spaces, you without any other mathematical background, you can think as a space of very smooth functions, essentially. And it turns out that you can use this space of very smooth function as a function class when you want to do statistical learning instead of, for example, linear models or these kind of things. And it turns out that they're very amenable to computational optimization. So it's really easy to actually compute the optimal function that minimizes the convex risk, for example, in this function class. So it's a function class that's very widely used in machine learning. And it's essentially, the reason it's so computable, so amenable, is because it consists of space of very smooth functions. And it turns out that you can do a lot with this. And in particular, you can also use these reproducing kernel Hilbert spaces in order to construct probability divergences between that compute notion of distance between two probability functions. And the most famous instance of this that relies on RKHS is the maximum mean discrepancy. So the maximum mean discrepancy computes this as it's written in this slide, the maximum difference in mean between two probabilities, P and Q. And this maximum difference in mean, you look at the maximum difference over functions in an RKHS that have maximum norm of 1. That's the way to compute it.
Yeah, sorry. Is anyone else seeing the correct slides? Or because
I'm only seeing the first slide.
Yeah, me too.
Problematic.
Right, now, yeah.
Okay. Yeah.
Can you see it here?
Yeah.
Perfect.
Okay, but somehow full screen in presentation mode, it doesn't work. Okay, let me just retry really quick the presentation mode and let me know if that goes all right.
Yeah.
We're still stuck on the same slide as before, I think.
Okay. Okay. So I guess I'll do so I guess I'll stay not in full screen mode. I'll stay like this.
That's all right.
Yeah, that's all right.
It works, yeah.
Okay, great. Okay, so now hopefully the definition of the maximum mean discrepancy is clearer. So as I said, it's a probability divergence that is computing by trying to find the maximum difference in mean between two probability P and Q. And the maximum difference in mean is searched over functions in a reproducing kernel Hilbert space that have maximum norm of 1. And in RKHS, the norm controls the smoothness of the function. So typically, a function with small norm is a very smooth function. Because of the probabilities, the properties of probability in kernel level space, this maximum has actually a closed form optimum. The proof is very simple. You just have to apply the Cauchy-Schwarz inequality in H. Because you actually rely on...
Sorry, I was sitting here yesterday and
yeah, I'm giving a talk right now. You can use my my office actually.
Okay, no
just right here and to the. Is that okay?
Yeah.
I'm very sorry about that. Sorry about that. It's very crowded in Gatsby right now. It's very hard to find places with.
Same here.
So as I said, because of the restriction of this objective to function with very small norms, the MMD is always finite for any PNQ, for any probability divergence PNQ, and that's a property that's not true for like many probability divergences. For example, the KALE is infinite as soon as PNQ have Disjoint supports, and it turns out, so as a very technical point, but it turns out to be quite important in generative modeling. The maximum mean discrepancy metricize the weak convergence of probability distributions, not exactly the weak star convergence, but as I said, it's kind of a small technical point. The function that maximizes this objective, we call it the witness function. So this kind of F star. And so in that case, for example, a very simple case where I compute the MMD between two Gaussians, P and Q on the left, you can look at the form of the MMD witness function. So that takes this kind of like, two, like a big ball and then two small curves on the sides. So this, we call it the MMD witness function.
So maybe if I can give a bit. So if you are familiar with GAN, so this F, it's something a bit similar to the discriminator in an adversarial network.
Exactly. Yeah, so it turns out that actually for MMD GANs, the discriminator, so the formulation, the variational formulation of MMD GAN is a bit complicated. But typically, and I don't know if I made it very clear here, but the MMD is part of what we call integral probability matrix. And integral probability matrix always try to compute essentially a maximum difference in mean, but they change in the choice of the function class that they rely on. So typically here we choose functions in a reproducing kernel space of norm 1 or below 1. But for example, for Wasserstein, you will use functions that are Lipschitz. And in that case, typically, in Wasserstein GAN, this function, this optimal witness function, is exactly the function that's computed by the discriminator. In the case of the MMD, it's a bit more complicated because actually, so as I said, the function for the MMD has actually a closed form solution. So you don't really need a critic to do that. But instead, what you do, because the MMD is a bit weak, is that you try to maximize not only the MMD, but you actually try to maximize the MMD over a various number of RKHS. And the critic is going to parameterize the RKHS. It's a bit harder to explain as opposed to Wasserstein GAN, which are really textbook application essentially of the use of integral probability matrix.
So what did you say? RKHS?
RKHS, which is like probability.
Oh yeah, okay.
Yeah, sorry. So I'm going to use RKHS quite a lot. So
yeah, okay.
If that's not clear, please tell me. Is anything unclear so far? Please feel free to.
It's clear to me.
Great. Okay. So let's now move on to the Kullback Leibler divergence. So the Kullback Leibler divergence is a probability divergence that's very ubiquitous in machine learning. So you typically see it in mutual information estimation or maximum likelihood or even variational inference. It's part of the larger family of what we call phi divergences that compute this an integral essentially of a function of the density ratio dp over dq with respect to q. And phi has to be convex and also has to satisfy some mild continuity conditions. So you have plenty of other phi divergences, and the KALE is the one with t log t as phi. The KALE is very sensitive to support mismatch in the sense that as soon as p and q are mutually singular, then the KALE between p and q is plus infinity. You can, in a sense, and that's it's a bit hard to explain in the first slides, but you can, in a sense, also define this notion of witness functions for the KALE. So the witness function here, you can see it as the log density ratio log dp over dq that is computed in expectation over dp. And when we will look at the variational formulation of the KALE divergence, it will make even more sense. But in a sense, the log density ratio here is kind of an analogous to the witness function if we want to make analogies of the maximum mean discrepancy. So here you can see it as when computed with like two Gaussians of different standard deviation. As I said, the KALE and the MMD have their own strengths and issues. So the MMD is well defined for an EPQ, but not super sensitive to support mismatch, especially for various choice of kernels. Essentially, it depends on the sort of the kernel, which characterizes the RKHS, but it can be not sensitive to support mismatch. Whereas the KALE is very sensitive to the support mismatch, but in a sense a bit too sensitive, since as soon as P and Q are mutually singular, KALE and P and Q is plus infinity, indistinctly of the distance to the support. Here is the, for example, is an illustration of the lack of sensitivity to support mismatch. So here we're computing the gradient flow between P and Q. So here actually it's a bit misleading, but P is characterized by this orange point. So it's an empirical probability distribution that's characterized by these orange points, and the Q is the blue circles. And so you don't need to really understand it right now what is the gradient flow is, but you see essentially that the goal being to match P to Q over time. You see that the MMD gradient flow has a bit of trouble actually achieving this, and the reason is exactly because of this lack of support sensitivity. So you see that the P essentially is exploding and not recovering exactly the target support, so the distribution Q support. So now that we have all this background in mind, I'm going to explain how to construct KALE, which is the probability distributions, the probability divergence that we investigate in our work. So it turns out, and I've not said it before, that the KALE has what we call a variational formulation. So you can compute the KALE as the supremum of a specific optimum, of a specific objective function. So if we consider C0b be the set of continuous and bounded function in RD, then you can show that the KALE solves actually the supremum problem here. If KALE is actually finite, then the supremum is reached at a specific point. And this point is, so it's a function, right? And it's the log density ratio. An informal derivation relies on what we call Fenchel duality. So if you're familiar with Fenchel duality, then the derivation should be very simple. If you're not familiar with Fenchel duality, then it's going to sound very obscure. But essentially, the proof is just a couple lines if you just want to remain at kind of a formal level. Now that we have access to the variational formulation of the KALE, we can construct the KALE. The intuition of KALE was to say, all right, so the KALE is not very smooth in the sense that it can be really quickly plus infinity as soon as there is mismatch in support, because we allow this log density ratio, this kind of like supremum. So remember F here, I think the supremum of the log density ratio, we allow F to be very not smooth. So typically F can be plus infinity and minus infinity in the case where P and Q have mismatch support. And in that case, that's where the optimal F is going to look like. If we want to have a probability divergence that's a bit more smooth, what we can do is try to restrict this supremum problem to a space where there are only smooth functions. And because of that, you will not be able to reach, for example, in the case where P and Q are mutually singular, this plus infinity minus infinity optimal function. And so that's exactly what we did. We restricted the variational function class to be an RKHS, which, as I said, is a space of very smooth function. It can, however, not be enough actually to do this restriction because H can actually be dense in the set of continuous and bounded function. And so because of that, it will be able to retrieve this supremum. And because of that, we added a strongly convex penalizer, which is an RKHS norm to the objective. And now, because the objective is actually strongly convex, you are ensured that you actually have a max and not a sup. And as soon as you have a max, then that means that the objective actually reaches a maximum. And by definition of a maximum, that means that it is finite. So as I said, the strong convexity of the RKHS norm ensures the existence of a maximizer. As I said, also, small norm in RKHS implies high smoothness. So if you add this norm penalty, you ensure even more, essentially, that the log density ratio estimate is going to be very smooth. Similarly to the KALE or to the MMD, we're going to call this optimum function the witness function. And we're going to see that the witness function kind of interpolates actually between the witness function of the KALE and the function of the MMD. The reason behind this 1 over plus lambda scaling that's kind of proportional is going to be made clear soon.
So I work quite a lot with Gaussian processes, and I wonder if we have a different notion of smoothness. Do you need what do you mean by smoothness? Because for GPs, there are plenty of kernels that give you non-smooth functions,
Yes,
regardless
yes,
to the norm.
definitely. So typically, if you consider Lipschitz kernels, if you consider kernels that are Lipschitz, then you can like do a quick back of the envelope calculation to show that actually f is also Lipschitz, a function in RKHS, and the Lipschitz constant will be bounded by its RKHS norm.
Okay, so you want kernels that ensure smoothness, because it sounded from the talk that all of them do, which is
no,
not the case, right?
that's true. That's true. So typically, for example, the Gaussian kernel or the so bounded like the Gaussian kernel, for example, will enforce a lot of smoothness.
Yeah. Okay.
Lipschitz kernel in general enforce smoothness. But that's true. Very good point. Thank you very much. And so now, yes, so now we have three probability divergences, so the MMD and the KALE, which are well known, and the KALE. And as we see here, the KALE witness function that I'm putting here in the middle kind of interpolates between the MMD and the KALE. So there is a, so we see some kind of pattern happening. And I'm going to make this this proposition a bit clearer later. And actually, in this slide, what I'm arguing is that I will show in the paper that the KALE interpolates between the KALE and the MMD. So as you set lambda to 0, the KALE retrieves the KALE. And that should be very clear, given the fact that the definition of the KALE is actually just a smooth version of the definition of the KALE, where we add this complexity penalty. But as soon as H is dense in the space of continuous function, if you tend lambda to 0, then you retrieve exactly the objective of the KALE. So this part should be pretty intuitive. The other regime, which is also interesting, is the case where you actually enforce maximal smoothness. And when you enforce maximal smoothness, then you retrieve the MMD squared. So the KALE actually approximates the MMD squared. And so the KALE is really a probability divergences that has this smoothing parameter that interpolates between the KALE and the MMD. And so now we understand where this 1 plus lambda scaling comes from. It comes from the fact that we don't want KALE to be degenerate as lambda goes to 0, as lambda goes to plus infinity. So if lambda goes to plus infinity, actually KALE is going to go to 0 uniformly. And so we need this 1 plus lambda scaling in order to actually obtain a non-degenerate form that interpolates correctly with the MMD. So that's the origin of this 1 plus lambda scaling. We also study in the paper the geometric properties of KALE and show that they are quite similar to the one of the MMD. So first of all, KALE between P and Q is finite for any P and Q. And also KALE metricizes the weak convergence of distribution, which is the same convergence that is metricized by the MMD. The KALE, however, doesn't metricize it. So essentially for any lambda that is positive, the KALE is MMD-like, but it recovers the KALE as lambda goes to 0. So I'm not going to discuss a little bit how can KALE be used in generative modeling. So I'm going to give a little bit of background in generative models. So we have hinted this a little bit in the discussion at the beginning, but as we're going to see, probability divergences are central when training GANs. So GANs, what are they? At the core, GANs are what we call implicit generative models. So implicit generative model transform a base distribution, so U, for example, a very simple distribution like isotropic Gaussian, by transforming them samples, by mapping the samples of U, using a generator G theta that is usually parameterized by a neural network. And that results in a probability distribution P theta that is the push forward, we call it the push forward of the base distribution U. So you are familiar with the normalizing flows in this group, I assume. And so the main difference between here normalizing flows and GANs is the fact that GANs are not defining bijections. And because they're not defining bijections, they don't have a probability density. And usually their support is located on a low dimensional manifold. And the reason is that the base space, so the space on which U is defined, is a space that's very low dimensional, usually, for example, like 48 or 64, whereas the output space on which P theta is defined is very high dimensional. It can be the space of images, so dimension 1 million. And because of that, by definition, G theta will never be a bijection between the input and the output space, just by difference of the dimensions between the input and the output space. So that's the main difference between normalizing flows and generative models, and that has massive implication, in particular because that means that you can't use the chain rule of probability, and that means that you can't access there is no density. P theta doesn't define essentially a density with respect to the Lebesgue measure, which is important. The biggest challenge of GAN actually arises from this. It means that you can't train GAN using maximum likelihood. It's not possible anymore. And instead, implicit generative models are trained by essentially playing a game between this generator network and a discriminator network. So the discriminator networks try to discriminate, so easily distinguish between true samples on which you're trying to fit generative models, and GAN samples, which are the GAN that are sampled, the samples that are sampled from your GAN. As you iterate over time, so you have this kind of min-max problem, the generator is going to get better and better. And it turns out that the intuition behind why this generator is going to get better and better is that under simplifying assumption, you can rewrite the inner maximum problem, so the maximum problem of the discriminator, as actually a problem that computes the Jensen sign divergence between the GAN and the true samples. And that's one of the key insights that appeared in the original GAN paper that kind of frame actually GANs as divergence minimizer. But instead, for example, as opposed to normalizing flows that kind of relies on the notion of like KALE divergence to minimize the to being fit. Here we don't use the KALE divergence; we use a weaker divergence. So in that case, the Jensen channel is actually not that weak, but it's because this theorem is made on a very simplifying assumption. But from this original kind of realization, a lot of then follow-up papers have been published that consider GANs that are actually minimizing other divergences, such as the MMD or the Wasserstein or the Wasserstein distance or even other divergence. And what is quite neat is that because the MMD and the Wasserstein GAN, etc., all admit this kind of like maximum variational formulation, you retrieve this kind of like generator discriminator network. But the discriminator now actually doesn't exactly try to classify between the true and the GAN samples. What it does is that it actually computes this divergence that you were concerned about, so the MMD, and that's what we call now a critic network. So usually there is this term critic network that is used instead of discriminator networks when you look at GANs, for example, like MMD GANs or Wasserstein GAN or this kind of thing.
Yeah, but I mean, in practice, it's also discriminating, right? You can use those values for.
It's the same thing, but yeah, essentially, I've seen quite a lot of time this term critic used, and I guess I guess it's related to this understanding of GAN as kind of like as divergence minimizer. But maybe this is. I
always found maybe it's a bit of a tangent, but I always found a bit annoying when people mention that these divergences, because the constraints that they have in their architecture by far dominates the constraint that is actually in the theorem.
Yes.
Like in the Wasserstein GAN, Lipschitz.
Yes.
That's a very loose constraint, and then you're using a very structured neural network that is smooth and whatever.
I actually agree with that. I agree with that. No, I think at the end of the day, the intuition, I think, spurred a lot of good projects, but it's true that there's probably a discrepancy between what would really be like the Wasserstein GAN, like a Wasserstein GAN training if it were like a theoretical Wasserstein GAN, and what we see in practice. No, I agree. I think that's a very fair criticism.
It's actually not that I mean, you can, for small cases, you can actually compute it.
Yeah, but yeah, for example, for the MMD, so typically the MMD, the discriminator has a closed form, so like the variational formulation is a bit more complex, and I mean that's yeah, it's the picture is not as simple as I'm presenting on the slides, right? But hopefully this gives a little bit of intuition. So typically, because as I said, the input space has a very low dimension and the output space has a very high dimension, the output distribution doesn't have a full support. And so you couldn't, for example, learn a GAN using the KALE divergence between the true and the GAN, so the GAN distribution and the true samples, just because these two distributions will be mutually singular. And so because of that, the KALE will be systematic plus infinity, and you wouldn't have some form of gradient signal to train your GAN. So this is not possible. On the other end, you can use the MMD because the MMD is well defined for any PNQ, so you can use the divergence that is the MMD. But the MMD can be quite insensitive to PNQ discrete passive support, and this can harm training. And so we kind of argue that the KALE can combine the best of both worlds, because the KALE, as we will see, so right now it's kind of an hypothesis, but we try to retain this property of the KALE that is sensitivity to support, but still by being well defined for any PNQ. And actually this work was pioneered, so in a kind of like a different way, but using very similar idea by this paper, Novozin et al. Of FGAN. But there was a quite more recent usage of actually KALE-based generative models in this generative energy-based model paper by Michael Argo that preceded our paper. The references will be below. So that's essentially one of the main applications of KALE, so in training generative models. So far I've been a bit, so I've said, oh, you know, because the KALE interpolates between the KALE and the MMD, the KALE will be kind of sensitive to like support mismatch, but I've not actually proved that this was true. And so the next part of this talk is to actually convince you that this is true by looking at a specific object, which is the Wasserstein gradient flow of KALE. And which I will motivate quite deeply, and I think the Wasserstein gradient flow of probability divergences are an object of clear interest in machine learning. So I hope that will be made clear by the end of this talk. So as I said, the goal is to validate the hypothesis that KALE is sensitive to support mismatch, and the investigation will be done on Wasserstein gradient flows. And first of all, what are Wasserstein gradient flows? So are any of you familiar with just gradient flows first? So okay. So I'm gonna quickly explain. Okay, great. So I'm gonna quickly explain it. So gradient flows are solutions to the following differential equation that you see here. And so if you discretize this differential equation, you retrieve exactly gradient descent. So gradient flows in that sense are the continuous time limits, are the trajectories that are the continuous time limits of the gradient descent updates for a specific functional f. So it's and usually studying gradient flows because they're not sequences, but they're actually trajectories, continuous trajectories. They can be a bit simpler to analyze because you don't have this kind of like discretization that can create some errors or some approximation error. And so gradient flows have been quite studied in order to get, for example, guarantees on optimization. That's kind of a classic thing to look at. Wasserstein gradient flow try to extend this notion of a gradient flow, but to the space of functions of to functionals that are defined themselves on probability measures. And so the problem is that probability measures are not Euclidean spaces, and even worse than that, they're not Hilbert spaces. And because of that, they don't have a notion, they don't have a predefined notion of gradient as you have in Hilbert spaces and non-Euclidean spaces by identifying the dual space with itself. So in Euclidean spaces, you really have this notion of gradient that spurs from this identification between Euclidean spaces and their dual. And you don't have this as soon as you move to metric spaces, for example. And because probability distribution can be, the space of probability distribution can be made metric spaces, but not Hilbert spaces, you don't have this notion of gradient. There has been a lot of work that has been actually done to extend this notion of gradient flow to more abstract spaces, such as metric spaces. And one of them are Wasserstein gradient flows. And I'm going to explain why actually this Wasserstein part is crucial in machine learning. There could be other kind of gradient flows, but the Wasserstein gradient flows are the ones that are useful to look at for many machine learning applications. So similarly to this first equation, you can define, so as I'm going to show you, can define these partial differential equations where the operator on the right is we call the Wasserstein gradient of a functional f defined on the space of probability measure. And so typically in our case, since we look at the Wasserstein gradient flow of KALE, we will take f to be KALE between some any distribution p and a target probability measure q. And so as a gradient flow try to, let me explain it in this slide actually. So what are the two important properties of Wasserstein gradient flow? So the first one is that we're going to actually move the probability distribution pt that is the analogous of theta t, which would be, for example, an Euclidean parameter. Here now it becomes a probability distribution, and pt is going to move over time in a way that is continuous in the Wasserstein geometry. And trajectories that are continuous in the Wasserstein geometry in the space of probability distribution are trajectories that do not create or destruct mass. They can only be moved continuously using a velocity field. I'm going to make it clear in animations later. The second property of a Wasserstein gradient flow is that it maximally dissipates. So this is also typical in gradient flows, right? Wasserstein gradient flow maximally dissipates a functional at every time t. So this intuition is similar to the intuition in Euclidean gradient flow. We're trying to maximally dissipate the objective. In the same manner, Wasserstein gradient flow maximally dissipates this functional f at every time t.
So why do you use the word dissipate?
Dissipate because I mean, it could be also decreases in a sense, right? Is because in a sense there is a sense of like the classic way to look at is to look at the derivative of the value f over time, and not the gradient, but derivative over f over time. And so there is this kind of like notion of energy dissipation. I would say it's just a semantic tradition in literature. But yeah, you could understand it as just maximally decrease. Yeah. And so if you wrap up these
That's the kind of linguistic barriers that make the translation difficult sometimes.
Yeah, I'm sorry. I wonder if there is some deeper motivation for dissipation. I don't know. There is this notion of infinitesimality, maybe like dissipation is kind of an infinitesimal. I don't know. No, it's yeah, hard to justify. Yeah, sorry if this made it unnecessarily obscure. But anyway, so if you combine these two constraints that we want to put on the notion of Wasserstein gradient flow, you obtain, and I'm not gonna make the derivation, but you're gonna obtain this. You're gonna obtain this continuity equation. That is the one that spurs from the first property. So the continuity equation enforces that you don't create or destruct probability mass in space over time. And actually, in order to maximally dissipate or decrease f, you're going to use a specific velocity field. And this specific velocity field can be understood as the Wasserstein gradient of the functional f. So here is an example, for example, of a trajectory of probability distribution that is not continuous with respect to the Wasserstein trajectory. So here you have destruction of mass on the right, and you have creation of mass on the left, right? Similarly here, you have in the continuous version, you have destruction of mass on the left and construction of mass on the right. So this is not continuous. So typically this couldn't be Wasserstein gradient flow trajectories. Here, however, is a probability distribution, so an empirical probability distribution that is continuous in the sense that all the points are moved by the velocity field. And so at no point you have a point that is previously created or previously destructed. All these points keep the same mass. And so because of that, this trajectory that you just saw is a trajectories of discrete probability distributions that are essentially point clouds that move over time in a Wasserstein continuous manner. And it turns out that actually the Wasserstein geometry is the right one to look at when analyzing GAN. And the reason, so I'm not going to make this formal in this presentation, but the reason is that GAN training curve. So let's say, for example, you're training a generator over time. This generator, so as you train the generator, you create a path of probability distribution. So probability distribution that are parameterized by your generator. And it turns out that this path of probability distribution is continuous with respect to the Wasserstein geometry. It's not continuous with respect to other, but with respect to the Wasserstein, it is. And as for Wasserstein gradient flow, GAN also tried to decrease or dissipate a probability divergence, right? And so actually Wasserstein gradient flows and GAN training are very similar objects. And there is one main difference that actually you pointed out in our previous discussion, is that for GANs, the probability distribution is parameterized by a neural network. While actually in our case, in the case of Wasserstein gradient flow, probability distribution aren't parameterized by anything. They're free to be anything. They're unconstrained. And so in a sense, Wasserstein gradient flow are the unconstrained analog of GAN training. It's as if you said, all right, I'm going to train a GAN with infinite power in my generator. I'm not constraining it anymore. Essentially, that's the idea behind Wasserstein gradient flows. And so if we look at, for example, Wasserstein various flows for various divergences, then we can get insight on the inductive bias of different GANs by understanding what's the impact of the probability divergence on GAN training.
So, but one just give you data memorization at that point?
I'm sorry?
Isn't it just going to converge to the training set to just memorize it?
That's so actually not necessarily, just because the functional that you might look at may be non-convex and it might have local optimum or these kind of things, right? So ideally, in a sense, in that case, we would, like in discretization where we have just finite point cloud, we would like it to be. But it turns out that in many cases, the divergence that that you're going to look at is not convex, and convexity has to be understood in a Wasserstein sense. And as soon as it's not convex, you might not, for example, converge to the optimum. So it's not going to do it. And actually, I would also argue that what's interesting to look at is also the kind of the shape of the trajectories, because it's true in GAN training, you don't have an ideal case, so you will never converge to actually memorize. You will not memorize the training sets, and the way GAN are designed is actually made so that you will not memorize training sets as opposed to this kind of easy setting. But in Wasserstein gradient flow, you really have this. You can really just abstract away like this constraint and just look at the inductive bias essentially of the probability divergence. But what you said can be true for specific probability divergence. There is another usage of Wasserstein gradient flows in machine learning, actually. That is specific, I think, to the Kullback Leibler divergence. So it turns out that the Wasserstein gradient flow of the Kullback Leibler divergence is the continuous time dynamics of a famous sampling algorithm that is called the unadjusted Langevin algorithm. Or ULA in short. But typically, an unadjusted Langevin algorithm allows you to get samples from a target probability distribution P, when you need access to the log density of P in order to get samples from it. So actually not the log density, but the gradient of the log density. And that's the key point, because the gradient of the log density doesn't involve the normalizing constant of the density. And because of that, using the ULA allows you to sample from a probability distribution that is unnormalized. So it's a super important and celebrated algorithm in sampling.
But that's stochastic, right? While the gradient KALE flow is deterministic.
So that's actually another important point. So typically, what I'm saying, the ULA is the discretization of the KALE flow. It's stochastic, but the law of the stochastic process will be the solution of the KALE flow in a probabilistic sense. So the law of xt is going to be pt, and pt is the deterministic solution of the KALE flow. Does that make sense?
So the KALE flow is safe, but is it? Okay, but yeah, I understand what you mean.
Yeah. So the ULA is stochastic. It generates a stochastic process, and the law of this stochastic process is deterministic.
So the solution of the
and it's the solution of the KALE flow.
So the solution of the Fokker-Planck equation of the Langevin dynamics is equal to the path of the KALE flow.
So
right?
Exactly. So the solution of the Fokker-Planck equation is going to define the law of your stochastic process from the ULA.
Yeah. Okay.
Yeah. On the other end, so the MMD has also a well-defined gradient flow. And actually, it turns out that the MMD flow characterizes the dynamics of training a two-layer neural network in the teacher-student setting. You can see it in the paper of Lena Ishiza, for example, even though maybe it's not made super clear, but this is actually what's happening here is, for example, an MMD flow in the teacher-student setting. However, the convergence of the MMD flow can suffer from the MMD's flat geometry for choice of specific kernels, as for example, the Gaussian kernel. In this part of the presentation, I'm going to actually construct the KALE flow, and hopefully the KALE flow will kind of retrieve cool properties of the KALE flow while still remaining well-defined when you don't have access to the target density. Which is the kind of classic case that we look at, right? As soon as we don't have access to the target density, let's say we just have access to samples, then you can't run a KALE flow or you can't run the ULA just because you don't have access to the log density. But because the KALE doesn't rely on the log density, it just relies on, for example, it's well defined for a mutually singular probability distribution, then hopefully you can create a KALE flow in cases when you can't create a KALE flow. And by similarity between the two functional, you will actually retrieve some property of the KALE flow, but extend it to cases when the KALE flow is not defined. So we're going to see it a bit later. So first of all, in my project, I quickly show the existence and uniqueness of the KALE flow. And it comes from applying essentially the definition of a Wasserstein gradient flow to the case of the KALE. And because of that, we need to compute the Wasserstein gradient of KALE. This step is not actually completely trivial because functionals that are defined this way have not been studied a lot in the Wasserstein gradient flow literature. And so essentially this notion of Wasserstein gradients has to be reconstructed for this kind of functionals. So it required quite a little bit of work, and then that's what we dedicate some part of our paper to actually that. And the solutions, as we show, are unique, and this is more standard, and it relies on the semi-convexity of KALE. So essentially, KALE is not convex; it's only verify a weaker notion of convexity that's called semi-convexity, and this notion of convexity is enough to ensure unicity of the solution of the KALE flow. The other point of the KALE flow is that, as such, when you look at this equation, it involves intractable quantities. So this maximum here is not easily computable because PT here and Q may be, for example, continuous probability densities. And because of that, you can't rely on specific properties of a reproducing kernel Hilbert space that allow you to get easy optimization in finite time. So right now, as such, you can't essentially compute the trajectories of the KALE flow for an arbitrary P and an arbitrary Q. This is just not possible. Instead, what you need to do is you need to discretize P and Q. So let's say, for example, you have access to samples x1 to xn of P0, so the original P, and y1, yn of the target density Q. In that case, you can compute a surrogate gradient flow where you plug in, instead of having this like a population P0 and Q, you plug in their discrete analog, P0 hat essentially, and the Q hat. In that case, by property of reproducing kernel Hilbert space, you can solve this maximum problem in finite time. And it turns out that actually PT, the trajectory, remain just a discrete set of points for every time t. And because of that, you can also compute PT in a tractable manner, because PT remains discrete for every time. So essentially, the mass doesn't split. If you have n points, then over time, you will still have n points in your probability distribution. You won't have a continuous distribution or something. And so now we have kind of a surrogate KALE flow that we hope is going to be able to approximate any form of KALE flow, assuming that you have of KALE flow, sorry, as soon as you have sample from the initial density and samples from the target density.
So now yeah. It's a stochastic algorithm. So you will resample every time you. So
it's only stochastic in the initial condition and in the target. So you assume that, so at the very beginning of the flow, you sample from P0, you sample from Q, or you just assume that you have samples. So typically, like in the GAN setting, you just assume that you have samples, right? And then if you fix this, actually everything is deterministic. There is no stochasticity involved.
But so then of course you're biased.
So you're biased. Yeah, definitely you're biased. Yeah, it comes from the initial condition, essentially. So there is a bias.
So is the maybe, I don't know if you know, would the whole setup be tractable? So if you actually resample every time, would you get something that can you prove if it's unbiased, for example, or what the bias is?
That's interesting. I need to think more about that. I don't know exactly how that would play out in our proof, because so we are typically used to like kind of propagation of chaos proof where the stochasticity is fixed at the initial condition. But if you actually have more and more sample to times, and if you decrease the step size to 0, it might be that actually you, at least it might be that the bias is reduced on the target size. You still have this initial sampling of the initial probability distribution P0, and here there might be essentially an incompressible bias, I guess. But yeah, no, that's an interesting.
You could get an interesting sampling algorithm also for inference.
Yeah, although essentially the problem is that Q here is typically the target distribution. And so you're like, in general setting, you have access to a training set. And essentially, the samples Y1, Yn characterize your training set. And usually over time, I mean, in some settings, you can have access to more training samples, but in many settings, you just have access to your original training set. And you can't really resample from Q, right? So in that sense, you're kind of fixed with a specific training set. For the sampling of the original distribution, usually P0 is kind of tractable. So you can resample from P0 if you want. So that may actually maybe generate a sampling algorithm or this kind of thing. Yeah.
But also for the training set, ideally you want to use mini batches, right?
Yes. That's something that's possible to look at. Yes. It depends essentially on the size of your training set. I don't know if ideally you want to look at. In some settings, you might want to look at it. Yes, no, it's true.
I mean, if you want to do something
yes,
like large scale.
No, definitely. But in that case, maybe as opposed to if you have access, the difference between full training set and mini batch, maybe in the mini batch, you actually have some more variance to control as opposed to when you have access to the full training set. I don't know if that's like the fact that you're using mini batch is gonna decrease the variance or increase the variance. It's not clear what it's gonna do, or increase the bias or decrease the bias. But it's true now that in theory, that might be good if you could use mini batches. But that's not studied in, for example, in our guarantees. So in our guarantees, essentially, we fix ourselves to the full batch setting. And so in the full batch setting, you can control the discrepancy between the discrete paths of probability distribution and their continuous time analogs. And so you get kind of a classic propagation of chaos results, where the discrepancy between the continuous and the discrete trajectory is going to blow up over your number of iterations. But if you fix the number of iterations and if you increase the number of samples, then you can make this bound as small as possible. So it's kind of an intuitive setting where, provided that you have enough samples, then you can recover the continuous time trajectory with arbitrary precision on a fixed time interval. But as the time interval increases, then your discrepancy will always blow up, essentially.
Looks a bit of a hopeless battle, right? You have a square root fighting an exponential.
Yes, but it's not the same values, right? So here, n is the time, and large n is the number of samples. So
yeah, I know, but
independent. But it's true. Yeah, I mean, yeah. The problem is that essentially the errors accumulate really exponentially, whereas you wouldn't have any form of exponential smoothing as you increase the number of samples or something like that. It could be that this bound can be increased actually if you have additional properties on, for example, the functional that you're trying to optimize. But we didn't investigate these properties for the KALE, and so we can't get better bounds than that. But yes. No, it's true. The two parameters have a different impact in the bound, essentially. That's a rather classical result in propagation of chaos theory. And so now we can actually, now that we have access to a kind of a simulation of the KALE flow, we can actually look at what are the trajectories. So here is the MMD flow, as I've shown at the very beginning. That's not very sensitive to support mismatch. And here on the other end is the KALE flow. So on the KALE flow, you really have the KALE really enforces constant matching between the target and the source distribution support. And so because of that, you get much better behaved flows in some settings, right? For example, in this specific setting. And so in that sense, KALE could be in some setting, it might be that typically in the situation where your training data lies on on some manifold, it might be that it's useful to use KALE instead of the MMD in generative models, precisely because you're going to recover the manifold much better than, for example, the MMD does. So here the MMD doesn't recover the manifold of the density distribution, of the target density distribution. And note also that in that case, right, the KALE flow, KALE, is not defined. And the reason is that the target distribution and the source distribution, they have mismatch in support. And so KALE between P0 and Q equals plus infinity. You don't have signal, and the KALE flow is not defined. So this is a case where the KALE flow actually kind of generalize the KALE flow to a situation in which the KALE flow was not defined originally.
The simple question. Oh, also, I'm sorry if I'm interrupting all the time.
No, you can. Yeah, no. So I mean, the rest of the slides are kind of like a follow-up discussion, but we can feel free to interrupt right now.
So imagine the trivial flow that you get by smoothing out one distribution, like with a Gaussian kernel, and then you can have a smoothing coefficient. Is there any relationship between that and?
So when you say smoothing, would you say? So what you say, for example, it's like kind of the heat equation.
Yeah. So
in the heat equation, the probability distribution that you recover at the end, actually, the heat equation doesn't really converge to anything. I mean, it essentially diverges to something that's uniform over RD, right? So I wouldn't do. Would your goal would be to recover the target distribution, as in that case?
No, I mean, so you have your target distribution. You just apply the heat equation for a small amount of time, so you get a Gaussian smoothing on the target, and then makes the KL regular. So the KL starts leak out of the.
Okay, yeah, I see. No, it could be that there are similarities. It could be that there are similarities actually. That's a fair point. That's a fair point. The question is, will you? No, but I mean that's a reasonable point essentially. Like you can smooth densities.
So basically, it's what variation autoencoders do, right? They put a Gaussian. I mean, except for the variational inference part, but the likelihood comes from the fact that they put the Gaussian output, which is basically just smooth out the density. So it just does a bit of diffusion outside of the manifold.
Yes. I mean, to be fair, I can't guarantee that you will recover the same trajectories between the two, essentially. But what I mean, but it's true that there are essentially intuitively there are some similarities. But yes, no, I agree that some like variational encoders, they definitely have this kind of like smoothing thing when you add a kind of a small Gaussian at every point, essentially of f of z, right?
So also the nice things you have there is that you can learn the whole thing by maximum likelihood. So the smoothing factor is the variance of the Gaussian, which can learn by itself by maximum likelihood.
Yes.
And if you have the data exactly on manifold, it can actually be pushed to zero. So what it does is that it gradually transition, the lambda will gradually transition from high values when you need smoothing, potentially, I mean, that's very ideal, but potentially to zero, in which you actually went it gets exactly on manifold. So
for the case of the KALE?
For the case of the smoothed KL divergence.
Okay, yeah, but in a sense, in that case, there is also a notion of smoothing in the KALE, right? Which is a bit different, but it intervenes in this lambda parameter that makes it interpolate between the MMD and the KL. Oh
no, I get it. Now my point is that if you do that by smoothing the KL divergence, I have to say, you guys, you chose a wrong name. This is just too confusing.
Yeah, I know. It's kind of hard.
If you smooth the KL divergence,
yes,
you can actually learn the smoothing factor by maximum likelihood.
Oh, you can learn the smoothing factor.
Because that's the noise in the data. So if basically, the more your distribution fits the target, the more the smoothing factor is pushed to zero by maximum likelihood. So it's kind of automatic the way it will focus. It basically ideally, if the data lives on a manifold and you get proper convergence, which I mean doesn't happen in practice, but you will get that it will converge to the actual KL divergence because the smoothing will go to zero, and that's happen if you have zero prediction errors.
Okay, I know I didn't know this part actually, that you could learn the smoothing parameter of VAs.
Yeah, because it's just the smoothing parameter is just the variance of the.
Yes. No, but I assumed it was usually fixed. I didn't know. I mean, I'm not very familiar with the VA literature, so I assume it was usually fixed. I didn't know
it's often fixed. Let's say fixed makes the convergence a bit more stable. But theoretically, the attractive things of learning it is that they could converge actually to the low-dimensional manifold by pure maximum likelihood training.
Okay, yeah.
As far as the data is lower dimensional and as far as your model converges properly.
Okay. Now that's interesting. Yeah, no, I would say that there are definitely similarities, for example, between KALE and this kind of smoothing.
But also I'm sorry. In your case, wouldn't it make sense to anneal down the lambda parameter during training?
It might be that it makes sense. It's just that in that case, I would say it's just not the case of the paper that we built, just because the paper really looks at a gradient flow. And so in that sense, you have to keep lambda fixed just because the functional is defined by lambda. In the case where you actually want to train a generative model, it turns out that this lambda parameter, at least in the generative energy-based model paper, you don't really have this lambda parameter because I think that the constraint, like essentially the smoothness penalty intervenes in a kind of different way. And I don't know if the smooth, because the lambda is the smoothness penalty. But like in the generative energy-based model, essentially, like people rely on neural network and not RKHS because in practice, neural network can be more expressive. And so in that sense, I think this lambda squared RKHS norm is something that's specific to the RKHS setting. But in the neural net setting, I think the smoothness is enforced in a different way. And I wonder actually if in the paper they adapt the smoothness parameter to 0 or not. But that's true that in theory it could be adapted. In theory, you want it to be kind of like high at the beginning in order to like be very smooth at the beginning and then like be low and lower and lower. Yeah, it would make the analysis more complicated, but I think in practice it's like what you want. I agree. It's an interesting point. Yeah, I think I'm out of time. I had like just 2 slides of like kind of opening because there is like essentially the gap is not completely closed in theoretically speaking. There was like a few things that I wanted to explore, and it's kind of like my follow-up work. And I'm not completely done on that follow-up. There is just like ideas that I have, but I think we're over time, so I think.
Thank you very much. I also apologize for keep interrupting you. It's that I'm not super fresh into this literature, and then I thought it was useful to have a conversation.
Oh, no, that's great. No, that's I'm very happy to be interrupted. Very happy to be interrupted.
Looks very nice work. I really wish people to put the effort to translate this for this kind of theories for the more practical machine learning community, because I still see that there is a decent divide, and sometimes it's just terminology.
Yeah. It's easy to be like in your own circle and not realize actually like for example just me assuming that RKHS are ubiquitous, like it's a classic mistake, and
but because I don't think it's a very strange thing, it's just that people is unfamiliar with a lot of
no, and actually I think there is also, I mean, it got some like recent momentum essentially because it was analyzed in the setting of training 2-layer networks. And if you analyze 2-layer network, essentially you can reframe the training of 2-layer network as optimization in the space of measure, when the measure is the measure on your space of hidden neurons. And actually this framing allows you to get very nice global optimization guarantees, etc. Okay. And so that spurred a lot of essentially re-interest in the theory of Wasserstein gradient flows, because there was a lot of new theoretical result that happens in the last 3-4 years that were very very interesting and had a lot of impact. Of course, it's like a 2-layer networks, right? It's not deep networks, but it's still it was still very beautiful work.
Steps. Okay, thank you very much. It was a really beautiful presentation and cool. Great work.
So thank you very much. Thank you for inviting me, and I hope that was clear.
More or less. All right.
Just
bye.
Thank you. Bye.